PCN tours the Keystone State, taking you inside Pennsylvania's factories, museums, and historical sites.
Hi, I'm Joe Piccioni, plant manager at J&L Specialty Steel plant in Midland, Pennsylvania. And today you're going to have the opportunity to tour a stainless steel plant to see how stainless is manufactured. It's used in many applications every day in your household and in your daily lives. And here's our display case with some examples of the end products of stainless steel. And one primary example is the fork that you eat with each day. As you look through our display case, you see a variety of products from this flatware to hubcaps, beer kegs, pots and pans that you use in your kitchen. We have truck mirrors, sinks, industrial applications, pipes and tubes are used in the petrochemical field. Other applications are dispensers that could be used in lavatories. Automotive exhaust systems are manufactured today mainly with using stainless steel for the exhaust pipe, the catalytic converters, mufflers, tailpipes. The best automotive exhaust systems are made of stainless. And it provides corrosion resistance, a high temperature, it's lightweight, very durable product. We also have caskets that can be made of stainless. So today we're going to tour our plant and get an idea how the basic stainless product is made. We're out at the main plant entrance of the Midland plant, where you see both the American flag and the French flag flying. The symbolism of that is we are a subsidiary of a French company called Usinor, which is the third largest steel maker in the world, with facilities in Europe, South America, North America, and the Far East. Our plant is a secure operation where all entrances through gates that are protected with security guards. The emphasis in our plant in the manufacturing is safety, as you see by our sign, and we want to welcome the PCN audience to our plant and to find out basically how stainless steel is manufactured. Okay, we're now in our scrap yard where our stainless steel making process begins. You can see in the background the engine bringing a carload of scrap into position to get loaded into the scrap bucket. In addition to running a steel plant, we also run a railroad. We have a subsidiary railroad, the Midland Terminal Company, that receives all the rail cars, scrap we purchase from suppliers and distribute them through the plant. They also handle all our movement of slabs internally and also receive coils. So we're going to start the steel making process with loading of the scrap. And this simple diagram describes the basic stainless steel making process. We're loading scrap from rail cars to the ground into a scrap bucket. The scrap bucket is taken inside the shop and put into an electric arc furnace. The roof lifts and swings to the side, allowing the scrap bucket to deposit the scrap inside the furnace. We close the roof, bring the carbon graphite electrodes down, and we start through the electrical charge to melt the scrap. When the scrap is fully melted, we tilt the furnace to pour the metal out into a transfer ladle. And then we then go to our AOD operation, which stands for argon oxygen decarbonization. That's where we make our final chemistry, final temperature, make additions as necessary, and basically get the final chemistry we want depending on the grade we're making. From there we go to a ladle trim station where we induce argon in the bottom of the ladle to control the temperature, and we make some final additions there as necessary. We may do some wire feeding. From there we go into our continuous casting process which we'll explain to you a little bit further when we get to that part of our process later. Now you can observe our mobile crane loading the scrap from the scrap car into the scrap bucket. We use a variety of scraps, so you can use carbon scrap, we use stainless scrap, and we alter the mixes of the scrap that we charge depending on the grades that we make. In this particular case, we're going to charge from a rail car containing carbon scrap. Each rail car has generally around 100,000 pounds of material contained within, and we'll charge just about the full quantity of a rail car into a scrap bucket. In addition to scrap, the other raw materials that we utilize in stainless manufacturing are ferroalloys, chromium, manganese, silicon. Here in the background are our bins where we store these ferroalloys that are loaded into charging buckets and put it into the electric furnace along with the scrap to be our base materials for the manufacturing of stainless steel. So we'll move on ahead forward to the electric arc furnace. This is our UHP, ultra-high powered electric furnace control room. You see our operator, furnace operator, Danny Sirocco, is basically in charge here, operating the controls. We have two electric furnaces. We can operate them as a single furnace in series, or we operate them sometimes in tandem, as we are doing today. And we basically switch from one furnace to the other without power, with power on only one furnace at a time. What we're witnessing here is a box loaded with the ferroalloys that we saw from the bins that have been loaded into this dump box, and they're being dumped into the charging bucket so that at the same time the scrap's being charged, the ferroalloys are also being charged at the same time. We're now witnessing a scrap bucket being hoisted by the crane. It'll be moved to a position where it's centered over the UHP furnace. The furnace has had its roof lifted and swung out over the teeming owl. You may hear a siren in the background. That's a warning signal for all crane movements. Part of the safe procedures to maintain safety awareness. The bucket's getting into the charging position. We call these buckets clamshell buckets because they open like a clam as you see the scrap falling out of the bottom into the furnace. As we complete the heat, we want to check for temperature. In this particular grade, we're aiming for a 2,800 degrees Fahrenheit temperature. And that's the process that's happening right now. We call it an IP. They'll put an instrument in to get the temperature of the metal. Provided that temperature is okay, then we're ready to tap into a transfer ladle. And when we do that, we tilt the furnace. The furnace is constructed so that it's on rockers and it tilts forward and back. Before we tap, we'll go through a process which we call slagging off, where we tilt the furnace backwards and remove the impurities that come to the surface, top surface of the molten metal. That's part of the process that you'll witness next. Slagging off process, then we'll go through the process of preparing the heat to be tapped. Open the tap hole, which is located on the other side of the furnace, tilt the furnace forward, and tap the heat into a transfer ladle. You can see our utility man, he's basically opening a tap hole so that we can tap the heat. Use oxygen assist to be able to do that, and he's just completed that, and now we'll start tapping the metal into the transfer ladle. What you're looking at is molten stainless that's around 2,800 degrees Fahrenheit temperature. We'll fill the ladle with approximately 110 tons of molten metal. You hear in the background is the electric furnace power, which will keep the power on during the tapping process. So we're continuing to try to keep the metal hot and keep that consistent temperature. And to also ensure that we get all the metal that's in the furnace tapped into the transfer ladle. Now completing the tapping into the transfer ladle. From this point in time, we want to get a chemistry. So we'll take a test. It will be sent to our lab, so we have our chemistry at this stage of the operation. Here our utility measurements using the device to get a sample for our chemistry. And we also recheck the temperature. I've just got the temperature, now he's getting the metallurgical or chemical sample. That's called a pin test. There's the cup test. We use both to analyze chemistry. It's the second pin test. It's important that we know what the chemistry is at this stage of the operation, so that we'll be able to predict which alloy additions we need to make in our refining operation at the AOD, which is the next stage of the operation. Transfer ladle just moved into the center of the teaming aisle, and you can see in the background we have a ladle crane with the lifting device getting in place. It'll pick up the ladle and transport it to the next stage of the operation, which is our AOD refining operation. It's a 250-ton crane to handle the weight, not only of the molten metal, but also the ladle, plus the lifting device. From this vantage point, we're now looking at our AOD operation, our refining unit. It stands for argon oxygen decarbonization. And this is where we fine-tune our chemistry, reduce our carbon by blowing oxygen in combination with either nitrogen or argon into the AOD. We've completed the blowdown on the carbon. We're making our final additions. You see the dump box and conveyor in the back is tilting as the additions are made for our final chemistries, and the gases are being inserted through the twir pipes at the bottom of the AOD to keep the metal homogeneously stirred. The consistency and chemistry and final metallurgy. We'll mix these final additions into the molten metal. Again, we capture the fumes as they go up through the top of the accelerator into our fume evacuation system and directed to our bag house for collection. This part of the process, this final addition is sterile. It takes a few minutes, and at that point in time, the heat will be fully processed and refined and be ready for tapping into a teaming ladle. Teaming ladle or casting ladle is another term. I should mention that the grade we're making is type 409. It's for automotive exhaust system. and we're in the process of processing 7 heats in one continuous cast. The heat we're seeing in the AOD vessel is the 5th heat of that continuous cast. And as you see the ladle coming, transfer ladle coming down, it's bringing the heat that we had seen earlier tapped from the UHP furnace. It's going to get in position so that once the AOD taps, we'll be able to recharge the AOD and continue the process as we take one heat away from the AOD. We'll be charging the next heat. So the final addition stir is complete. The vessel is turned down. At this point in time, our utility man's coming down and he's going to get the tap temperature. He will insert the temperature measuring device into the furnace. The teaming ladle is getting prepared to accept the heat. The first thing we have to do is we go to what we call the bore fill station, and we dump some sand into the spout area where the material, where the molten metal will transfer through that through a slide gate into a shroud into the next part of the operation at the caster. So at this point in time, we're putting the sand in the bore fill station. The ladle has been preheated. You can see the reddish color in the background. We want to make sure that the ladle refractory is warm. You see the sand being added to the bore, to the spout area to provide some insulation and protection of the slide gate. Now that that has been completed, the casting ladle will move into position to accept the heat from the AOD. What we're doing right now is we're going to put a lid or cover onto the ladle, and it's for the purpose of being able to induce nitrogen into the ladle. Ladle cover is now in place. So we've got the ladle in position to accept the heat from the AOD. The cover's on to protect from nitrogen pickup. We will induce argon into the ladle to flush out any of the nitrogen or air, and then tap into the ladle. There's the argon hookup. Fittings now in place. Argon's flushing. And it commences. This teaming process is much quicker than the UHP. With a wide, large spout, the metal comes out very quickly. Will now disconnect the hose that we use for the argon purge. Okay, at this point in time, the ladle is going to be transferred to the trim station, the next part of the process. So we'll continue the still making process over there at that station. The ladle for the fourth heat has just been removed away from the tundish. We're taking the fifth ladle in this sequence. To my left here, we'll put it in the ladle stand and start teaming from that ladle into our tundish. Our tundish is a container intermediate between our casting ladle and our continuous casting mold. The tundish, you can imagine, is a large vat or like a large bathtub. We induce molten metal from the teaming ladle in one side of the tundish, and at the far end of the other side of the tundish is where we have a tap hole and a shroud that transfers the molten metal into the continuous casting mold. So the crane is just picked up the ladle and it's moving it to the position it will be in the on the ladle stand so we can continue the casting process. From the AOD operation and before the casting operation, we have a trim station, which timing-wise we had to miss today because of the interest of time. We couldn't wait for that to occur, but at the trim station, we basically induce argon to the bottom of the ladle, the purge plug, and we use it basically to keep the molten metal stirred, control our temperature, and also for our steel cleanliness. The argon stirring and bubbling helps to any inclusions that may be inside the molten metal float up to the slag surface. So unfortunately we missed that because of timing. From there, the teaming ladle comes over and is being put in position in the caster to continue our casting sequence in this case. At this point in the process, the slide gate is opened on the casting ladle, and we are again refilling the tundish. so that the casting process can continue in sequence without interruption. Casting in sequence gives a big advantage from a yield standpoint because we don't have head and tail losses between heats. So it's an efficient way for steel making, and it's not only for efficiency but for quality. We'll move to a different position now so we can get another look at the tundish and the tundish filling the caster mold where the steel making solidification process starts. There's about 20 tons of molten metal in that tundish, and from that tundish we drain through a shroud into our casting mold. You'll see the vibration and the movement of our oscillator. Oscillator starts the casting process. As the molten metal enters the mold, it chills from the outside skin towards the center. And the slab, as it's being poured, is advanced down through the machine. And water is induced to cool the molten metal so that to assist in the cooling process, and that also contributes to the solidification process. We now have a view from the exit side of the caster. From the upper level, the slab, as it's being poured, continues down through the casting machine and in the solidification process. In doing so, it curves. We're on a 41-foot radius curve. It brings the slab down through the machine, and it solidifies as it's being cooled, and it's now exiting the machine. At the exit end of the machine on our table run-out, we have a torch, a traveling torch, that will cut the slabs to specific lengths based on what our customer requirements are and what our orders might designate. Our casting machine will cast two different thicknesses, 6 1/8 or 7.5 inch thickness, and will cast as narrow as 26 inches and as wide as 62 inches. Now we view the torch cutting process in progress. The slab is traveling, and the torch is on a car that travels with the slab. And we cut to the prescribed length to fit the particular customer order. The next part of the operation, we put an ID tag on the slab as it exits the caster. It's extremely important that we maintain good identity by grade, size, so that we can maintain that identity through the hot strip mill and finishing processes. The next part of our process is slab conditioning. Some portion of our product mix, depending on grade, requires that we grind the outside surface of the slab and remove the scale from the slab, and we do it with these 6 grinding machines. We grind approximately 50% of our total product line. These machines traverse up and down the slab, and as you see, it's a grinding operation, and the outside scale is removed. That material is collected, gathered, and sent back to the melt shop for recharge because it has valuable nickel and chrome content in it. These slabs will be converted into hot bands that are anywhere generally from an 1/8 inch thick up to 5/16 inch thick and come back in a coil form. And the next part of our process is what we do to finish those intermediate hot band coils into finished final gauge stainless. From the hot strip mills, we receive back from the hot strip mills a hot band. And this is an example of what our hot band looks like. Darkened surface, and it's in coil form. And in our finishing process, what we do with these hot bands is basically run them through annealing and pickling lines to descale them, to soften them. We put them usually through pickling operations to clean them, cold reduce them, and once they're reduced in thickness through cold reduction mills, we send them normally through cold annealing and pickling line, temper passing, final edge trimming, and they're ready for shipment to the customer. In 1997, we commissioned a new operation at the Midland plant. It's called our DRAP line, which stands for Direct Roll, Anneal, and Pickle. And this little diagram gives you an idea of what we do. We take the hot rolled coil and we mechanically descale it by surface mechanically conditioning. We descale it with shot blasters and brushing machines. We do cold rolling through continuous mill scans, annealing, pickling. We also do skin pass or tempering, final leveling, and edge cutting. And all in the continuous process instead of being done in separate operations, which is done in most conventional mills. So the J&L DRAP line is the most modern stainless flat-rolled finishing operation in North America. There's a similar one that exists in France by our parent company, Usinor, in their Eugene division. They have a similar operation, and they're presently the only 2 in the world, and they're the most modern finishing facilities that exist in the world. We basically start that operation. This is the coil storage building where we can store